We occasionally get critiqued for some of our content being a bit niche, and while I agree that more production-focused tutorials are really useful to some of you, I kind of like those niche topics, as you can use them as kind of building blocks for bigger setups. However, today we're gonna go as niche as possible and probably as useless as possible for most of you out there. As for this to make sense, you'd have to have access to an embroidery machine, which I, by some circumstances, happen to have. And in an older tutorial, we already did virtual embroidery. That means virtually creating geometry that looks like it's an embroidered image of something. However, I've been constantly thinking about how and if I could pull off exporting Houdini geometry or Houdini paths, that means polylines, into a format that the embroidery machine reads. The particular machine I have access to reads DST files, which I've never heard of previously. Turns out DST files are somewhat of the lingua franca, so the universal language of embroidery machines. Sadly, however, they're a really weird format. And I have the feeling that most of the format specifications are based on what used to be punch cards. The files are a weird mixture of plain text and binary data. Also, the coordinate system or the increment system for giving coordinates is really weird. So I soon gave up on writing a converter or an export for this myself. However, with my recent interest of integrating more Python libraries in my Houdini workflow, I stumbled upon this thing here called Pyembroidery. And lo and behold, this is an import and export library for reading, writing and modifying embroidery machine files, amongst which we have the DST format. And if you set up your Python environment, as we did in one of our tutorials, and I'll link it in the description, you can just use this short command in your command prompt to install this library. And then the code needed to export polylines into this DST format and have them embroidered onto physical fabric is rather straightforward. So let's start off with a harmless demo by dropping down a geo node, diving in there, and maybe using a font node to just generate some outlines. Let's be egocentric about this and write Mo in here. The font doesn't really matter. I like bold fonts or even black ones. And in the font node, the only thing I'm going to do is uncheck whole faces. So we're getting rid of this dividing line here, which we have activated when whole face is checked. Let's ignore this weird geometry happening here, because what we're going to do now is convert this font. And in here, let's just increase the U and V resolution. And after that, let's use the ends sub to unroll with new points this geometry and thus generate outlines. Now, if I check the point display here, you can see that my points are distributed not really uniformly. So let's fix that by using a resample, which in this case, I'll set to something a bit smaller here, resulting in this point distribution. Next, for my embroidery export, it's important to scale this thing properly. And in Pyembroidery, 1 unit is 1/10 of a millimeter. And the particular machine that I have access to has a canvas size of, I think, 13 centimeters at max. So let's scale this to, say, fit within a box of 10 by 10 centimeters, leaving a bit of a border around it. I'm gonna do that by using a match size, which I'll drop down after. And in here, I'll check scale to fit. So this now sits within a 1 by 1 by 1 box. To scale it up to the desired size, I'll add a transform to this. And keep in mind 1 unit is 1/10 of a millimeter, so in here in the transform, to have this 10 centimeters wide, I'll scale it by 1000. And then over the viewport hit space and H to reframe this. So now we have our geometry, our individual points here, ready to export into a DST format. So after we pip install our Pyembroidery, let's use a Python sop here, which will attach to the transform. And the first thing I want to do here is import the Pyembroidery library like this. Seemed to have worked, no errors. And then after this header code here provided by Houdini, the first thing I need to do is to specify a pattern, which is the data structure into which we write the individual stitches to form the embroidery. Let's call this pattern, and it's a Pyembroidery emb pattern. So an embroidery pattern like this. Don't need the semicolon. And now what I want to do is iterate through all these individual primitives. So we've got 3 primitives here. That means 3 polylines, one forming the M, one forming the outer O, and one forming the inner O. I want to iterate through those 3 primitives. And for each primitive, I want to iterate through all of those points and write out the point positions into stitches, into the embroidery pattern. To access our individual primitives and points, we need to specify a few things. First, we need to tell Houdini's Python which attribute to access for reading in the point positions. Let's call this P attribute, and it should be equal to the attribute that we find when searching through our geo, and we want to find a point attribute by its name called P. And also we need to specify an iterator, which we can use to go through all the primitives. Let's call this one prim iter source. Could also call it just prim iter. And it should be equal to our geometry's iterator that iterates through all its prims, like this. And now what we can do is we can call for a variable into which we store each primitive that we're currently iterating over. And we want to iterate through all the prims that are in the prim iter source. And for each one of those primitives, the first thing we want to do is we want to access its points. We can do that by reading out its points. Let's store it into a variable called primpts, and it's equal to our primitive's points. Simply like this. Okay, so far no errors. And also I just want to have a counting variable that will increment while going through all the points. Let's initialize this to be 0. So what I want to do now is iterate through all the points. So let's call another for loop for p in prim PTS. The first thing I want to do is look up the position. So let's call this my pos, and it should be equal to p, that's our current point, attrib value, and then let's use the p underscore attribute, which we specified to look up the current point's position. Now for the very first point, what I want to do is add a jump stitch. That means when we're jumping from one primitive to the next one, we don't actually want to punch a stitch, but just move the needle over. So we're going to check if our counting variable, I, equals to 0, so if it's the first stitch, then we add to our pattern a command, and this is basically what I looked up in the Pyembroidery documentation. So we're going to add the Pyembroidery .jump command, like this, and we want to jump to mypos, the x coordinate, which is the first entry in the mypos variable, and then we want to jump to the second, the y coordinate, second entry in the mypos coordinates here. However, as I've discovered, the embroidery machine I have access to mirrors the y-axis, so I'm going to negate that like this. So that's what we're going to do for the very first position in each primitive. And if we're not on the very first position, we're going to add to our pattern a stitch with absolute positions. It's called pattern add stitch absolute. And in here as arguments, we're going to add a Pyembroidery stitch like this. And we're going to go to the current point's position on the x and negate it y. And after we're done with that, we'll increment I. So now we're writing out all those jumps and stitches into our pattern. And after we're done with that, going through all our primitives and all our points of our primitives, we'll have to tell the machine that our pattern ended now by adding to our pattern a command. And the command we're going to add is called Pyembroidery.end, telling the machine we can stop now and we are done. And finally, I want to write out the file we created containing that pattern. So I'm going to call a Pyembroidery.write, and we're going to write out the pattern, and then we'll specify a file path where we want to store this pattern to. So let me just copy this. I'll just point this to a location on my hard drive and put that in quotation marks. Important to specify this using forward slashes here, and then I just went with this silly name here, and that just comes from the fact that the interface on that particular machine I'm using is, let's say, a handful, and it helps to have your files popping up on top of a list. So that's why I appended these 3 A's here. And now that should be it. So let's save this and navigate to that folder I specified. And you can see I did a few tests already here. So let's open up this file we just wrote out. And we can see that is exactly this weird combination of plain text and binary data. So let's copy that onto a USB drive and try it out on the embroidery machine. See how and if we failed. And lo and behold, we can see a very coarse preview of what appears to be MO. Okay, that seemed to have worked. Now, a few more things if we want to embroider something a bit more complex than those individual 3 lines here. Say, for example, let's zoom out here a bit, and let's create a VDB into which we'll store a vector float, adding a VDB activate. And in here, let's scale this to be 8 by 8 by 0.1 units, so a rather large XY volume. Also up here in the VDB, let's call this thing V for velocity. After the VDB activate, let's use a volume VOP, dive in there, and let's fill this thing with a bit of noise. So let's drop down a unified noise. Let's use the static one. And this as an input down here takes the position, so let's wire that up to our P slot here. And then let's just delete this volume output here and instead set this to generate a 3D noise out of 3D input. And let's export this noise here by using a bind export node, which we'll set up to export a vector called v for velocity. And we're going to wire this in here like so. One more thing I'd like to do before writing this out to v, however, is multiplying this with a constant, and this constant should be a vector, and I want to multiply my noise so that it only points in x and y, so I'm going to multiply it by 1 on the x, 1 on the y, and 0 on the z, and wire this into the second slot of this multiply here. Okay, that's it. Back up, got a two-dimensional noise now here in my volume, and now what I want to do is append a VDB analysis and set this to calculate the curl of our noise. And now finally, let's create a circle into which we'll scatter a few points, let's say 100, and then wire those points into a volume trail in the left input slot with the VDB analysis into the right input slot, highlight this, and again press space and H over the viewport to zoom into here, and we can see that is not exactly what I was aiming for. I wanted to create this beautiful curl noise, and I think what I did wrong here is in this volume VOP, this multiply here. Let's just disable it for now, and instead, after our VDB analysis, let's drop down another volume VOP, and in here now, let's get rid of those two nodes here, and instead drop down a bind to import and a bind export to export our values, and both should be set to be importing or exporting v, which is a vector. So let's set both the import and the export to a vector, like so. All right, in here, let's multiply this velocity vector again with a constant that we're going to create, which we're going to set to be a vector, and again to be 110, like so. And now we can see we're getting this beautiful curl noise trails that we were expecting to see. The resolution is fine for now, I think. Let's uncheck the velocity visualization. And what we could do now is feel tempted to just wire this in, and maybe let's just take the resample with us to wire this in here. For this curves, it's sometimes wise to set the resample to treat the polygon as subdivision curves, makes them look a bit more rounded. See the points? Okay, that's looking good. And then we scale this to be 1 by 1 by 1, and then scale it up so it matches our machine's coordinate systems like this. One thing that will come out really weird now if I put this on the machine is the jump stitches. So we are having 100 individual streamlines here, and in between we are jumping from one line to another. We can visualize that using a join node in Houdini, which we'll set up to have a tolerance of 1, to not do any blending, to connect in U-space, connect the closest ends, and connect all primitives. So if we wire this up into the join now, we can see those are the jump stitches which mess up my pattern. And if you've got a machine that does automatic yarn trimming, you're lucky. You can just insert into our Python code after each primitive. So that would be down here. You can add a command here, which is called Pyembroidery trim, like so. However, my machine does not read this command. It cannot trim. The only way to get my machine to trim here is to add a color change, which is done by a stop command. However, that requires me to confirm a color change on the display. And you've seen the interface and you've seen how slow this is. So to do that for 100 stitches or so, 100 lines or even more is kind of impractical for me. So instead what I did is I just didn't add any trimming or any stops in here. However, I tried to minimize the distance of those jump stitches. So I tried to jump from lines nearby, which we can easily do by before wiring this into the Python or the join to visualize what we're doing on the machine is just adding a sort node like this in between our Python, and let's visualize what we're doing here with the join. So currently we're not doing anything because we're not resorting anything in here. However, what I want to do is I want to resort my primitives by spatial locality. So now you can see they are sorted in a way that the jumps when joining those are minimized. Still looks a bit messed up, but not as bad as previously. And now what I did in this case is I just wired in this joined geometry here, which is just one primitive, so one giant stitch here into the Python node and then put that on the machine. So that is the setup for today. On the one side, a very primitive, just a bunch of letters here spelling out Mo, and you can see the jump stitches here being visualized with the join. If you don't want that, just uncheck it and maybe insert the trim command or stop command here, depending on what machine you have. However, I like to leave this enabled. And then we just generated a really simple volume trail and use that for a bit more of a complex pattern that we can embroider now. So while I put this on the machine, infamous last words, I hope as always that you had fun. I'm aware that this is very niche and very few of you might have access or actual use for an embroidery machine. However, I still think there are some takeaways even if you're not really interested into embroidery. One is that by adding a few easily available Python libraries and writing really just a few lines of code in here. I mean, if you leave out these Houdini generated lines here and a few line breaks, I think this is under 20 lines of code. You can easily get tasks done, which previously would have involved a lot of work or maybe have been plainly out of your reach. And also when it comes to working with hardware, in this case an embroidery machine, you have to figure out its limitations. In my case, it took me a few days to realize that this machine does not recognize trim commands in between different stitches. And it took me another while to go through all of the hacks that the internet told me that might be possible with those machines to get them to trim. However, I think I'm pretty certain at this point that my only chance to get this thing to trim in between is to fake a color change, which again is impractical for my application here. And finally, I really love the openness and adaptability of Houdini so that I'm able to actually take these really nice paths or any two-dimensional geometry I create in Houdini and export them in a way that I'm able to recreate those shapes physically. In this case, not on a 3D printer, but on an embroidery machine. If you want to know more how to use Python within Houdini, how to get certain libraries working inside of Houdini, if you like what we're doing and plainly want to support us, consider becoming a patron of ours. And to everyone already supporting us, thanks so much, folks. It is with your help that we can keep Intagma up and running. With a very special thank you going out to Important Looking Pirates, Jellyfish Pictures, The Mill, Electric Theatre, Pixonic, Random 42, Rodeo Effects, Side Effects, Lusion, and Rafik Anadol Studio. Thanks so much for supporting us. So, as always, until next time, it is cheers and goodbye.